Okay, so here we have an example of a circuit where we have a ground in the circuit. And in the problem, we want to find the electric potential or the voltage at point A and point B. So how do we deal with circuits with grounds connected to them? We're gonna set this up the same way we normally would, and we are gonna figure out the current going through the circuit first, because it turns out that even though we have the ground connected to the circuit, it doesn't actually change anything about the current going through the circuit. In this case, if you want to deal with a problem where that's not the case, there is another problem. It looks like number 50, where there's two grounds connected to the circuit. That does do something weird. We'll have to do that example at some point. But when you just have the ground connected to the circuit, it's not really going to affect the current going through this thing. So we're just going to label the current I. And the reason why I have the current pointing in the counter or in the clockwise direction is because the 9-volt battery is larger. And notice that they are facing opposite directions. So I think the 9-volt would win. And so let's just start this problem by figuring out what the current would be. Okay, so the current of this thing, using Kirchhoff's loop rule, we know that the difference in potential of our circuit needs to be 0. So I'm going to start with the 9-volt battery. We have 9 volts. We're going to minus the voltage. We'll call this resistor 1. So minus delta V of R1. And then we would minus the 6-volt battery because we're going from a high potential to a low potential. So minus the 6 volts, and then we are going to minus the delta V of resistor, we'll call this one down here resistor 2. And Kirchhoff's loop rule says that all of this needs to equal 0. So I'm going to combine the 9 volt and the 6 volt to give us 3 volt. So we have 3 volts. And then delta V of R1, that's going to be minus I, the current, times R1. And then we are going to have minus I times the resistor of resistor 2, so R2. And so this should equal 0. And then I'll add the IR1 and IR2 to the other side. So we have 3 volts equals I times R1 plus R2. R1 is 2 ohms plus R2 is 1 ohm. And so we get 3 volts equals I times 3 ohms. And so solving for I, we get 1 amp. Okay, so now we know the current, and what we can do is we could figure out the voltage of each resistor, which we are going to need to figure out remember we're finding what is the voltage at A and what is the voltage at B, and we need those values. So delta V of resistor 2 of R2, this is equal to current times resistance. So this would be 1 amp times 1 ohm. That's going to give us 1 volt. And delta V of resistor 2, delta V R2, this is equal to resistor 1, which is 2 ohms, times the current 1 amp. So we get 2 volts here. Okay. So how do we figure out what the voltage is at A and B? So what the ground does is it sets the spot where it's connected to equal to 0 volts. And so this part of our circuit here, this part of our circuit, all of that is equal to, so before we go over any kind of component, this part of our circuit is equal to 0 volts. So that's what the ground does. It, by convention, the earth, which is the ground here, is set to 0 volts. So anything touching the ground is going to be equal to 0 volts. All right, and so what I'm going to do is move clockwise around this circuit, and I will add or subtract voltage depending on if it's a battery, what direction the battery is facing, and if it's a resistor, I will always subtract voltage. So as I move across the battery then, So as I go in this direction, then I'm going to add voltage. So now, when I'm in this area, I should be at 9 volts. So that means that V of A is at 9 volts. As I move across this resistor, I'm going to subtract voltage, so I'm going to subtract 2 volts. So now in this area, I am at 7 volts. And then as I move across the battery, I'm going to drop voltage again. I'm going to drop 6 volts, and so now I am at 1 volt. So that's where point B is located, so that means that the potential or the voltage at B is 1 volt. Okay, and so those are the two values we needed, V of B and V of A. Up here is 9 volts, so that's our answer. Just to check that we did this right, as I drop across the last resistor, I need to be back at 0 volts. And so I'm at 1 volt right now. If I drop across resistor 2, I drop 1 volt, and so I get back to 0 where I need to be. I have another example. Make sure you try it on your own first. 31.26 is also posted for you to try some more practice. And then we will, so at some point, try 31.50. I encourage you to give it a try on your own, see if you can reproduce the answer that I get.